Hello, welcome to this Architecture Today webinar on designing for extreme environments with content partner VMZINC. My name's Ruth Slavid and I am your host for the event. We're going to have two speakers today and then the opportunity for some questions. The first speaker is Hugh Broughton of Hugh Broughton Architects, who I will introduce properly in a moment. The second speaker is Jonathan Lowy of VMZINC, who's going to take us, I think, on quite a tour around the world, visiting virtually zinc projects. And then, as I said, we will have our questions. And if a question occurs to you at any time, just press the button and send it in. And I will be selecting the most interesting and pertinent questions to put to our speakers at the end. So that's the structure. And first of all, I'm delighted to introduce Hugh Broughton, who in the last few years has done some very varied award-winning architecture in the UK, but he certainly made his name not in the UK, but in the Antarctic, where he designed the Halle research station for the British Antarctic Survey and then went on to several other projects. He's going to be talking about those now. I've heard him talk about Halle in detail before, and I know we're in for a fascinating session. Over to you, Hugh.
Well, thanks so much, Ruth, for the introduction. I'm so pleased that you're chairing this event today because you've been such a fantastic supporter of our work in Antarctica, and we've actually worked with each other on quite a few occasions as you've written some really insightful articles and, of course, a great book about our work on the Halle 6 Antarctic Research Station. I'm going to talk about our work in Antarctica, which is actually a portfolio of projects which we've developed now over the last 15 years. So let's think about Antarctica just before we get started. Antarctica is the coldest, the windiest, and the driest continent on Earth. In the depths of winter, it has a population of just 2,000 people. So it's an extremely isolated environment as well. Yet it's also a source of fantastic scientific research. Some of the great investigations into climate change take place in Antarctica, led by some of the world's greatest climate change scientists. And it's in support of their work that our portfolio has developed. I'm going to talk about 5 different stations in which we've been involved, and I'll start with Halle, which is the British station at 75 degrees south. That places it around 900 miles from the South Pole. It's actually very southerly and experiences some quite extreme climate. It's very, very remote as well. This is the site of Halle 5, which was the previous station before the one we designed. Halle is unique in that it's located on a floating ice shelf. That means it's on ice, which has floated off the main continent of Antarctica and is actually supported on the sea. The Brunt ice shelf is 150 meters thick, and it's moving out to sea at approximately 400 meters per annum. And every now and then, it runs the risk of fracturing into giant icebergs. The previous station, Halle 5, comprised 3 principal buildings. Off to the right there, you can see what was called the Laws building, which was the main habitation building where people had their bedrooms, there were offices, dining spaces, and so on. And then there were 2 other buildings devoted to science, one for near ground science and one for outer atmospheric science. Halle is extremely cold. Temperatures in the winter plummet down to around minus 56 degrees Celsius, and even in the summer, they never rise above freezing. As the temperatures do rise in the summer, so the site becomes extremely windy as winds from the polar plateau fall down towards the sea, a phenomenon known as katabatic winds, creating wind speeds well in excess of 100 miles an hour, sometimes up to 150 miles an hour. And as they blow across the ice shelf, so they pick up small crystals of ice called spindrift, which basically sandblasts everything in its wake. It also means that everything that's left on the surface of the ice will quickly become buried by drifting snow. That could be a small spanner, or it could be something as sizable as a building. As a result, at Halle 5, which was an elevated structure built above the ice shelf, it was necessary to jack the building up every year by around 1 to 1.5 meters to enable it to essentially climb above the rising snow level. This was an incredibly labor-intensive process involving around 50 people. Here you can see them all suspended in scaffold baskets using electric screw jacks to gently increase the building's height above the ice and therefore protect it from being buried year on year. So it's cold, it's windy, it runs the risk of being buried by rising snow levels. The next challenge is that at Halle is that it's also dark for 105 days of the year. That's 105 days that the sun does not rise above the horizon. That's in the depths of winter when the crew is typically around 15 people. So one has to imagine, and we're all getting better at it as we exist through our current forms of isolation and lockdown. But there is a massive challenge being quite so isolated from the rest of the world in total darkness, living with just 15 other people. The environment at Halle 5 was something close to institutional. It was made up of a series of different rooms, a dining room, a separate bar, a separate lounge, arranged off a corridor. And it created some quite significant psychological challenges of people walking up and down the corridor, hearing other people having fun in the bar and just challenging themselves. Do I feel confident enough to open the door to go in and join the fun? Or do I feel too shy and I'll just leave them to it? And it really was quite a stressful environment for people to live in over those long periods of the winter. And at the time that we inherited the design of the project, people were living on base for up to 2.5 years without returning back to the UK. Their only neighbours are a large colony of emperor penguins who live around 10 miles away and which could be visited at the start of the winter season by the winter crew. Logistics was managed by this ship, the Sir Ernest Shackleton, shortly to be replaced by the new research vessel, the Sir David Attenborough. Everything that is needed to supply Halle is delivered around Christmas time and is unloaded onto sea ice, which is around 2 meters thick. It's then carefully dragged across the sea ice to the edge of the Brunt ice shelf, where the vehicles that were retained at Halle are used to manipulate the edge of the ice shelf to create ramps to allow all the supplies to be dragged up onto the ice shelf and then onwards to Halle to enable it to function for the remainder of the year. And of course, when we were considering the construction of a new station, we had to consider a similar path to deliver all the materials to the site. So against this background, one might ask oneself, why do the British Antarctic Survey need to operate a base at a place like Halle? And the answer is really simple. It's because the science which is conducted at stations like Halle is of world significance in our understanding of the challenges of climate change. Just by way of example, in the mid-1980s, it was 3 scientists working at Halle who first discovered the hole in the ozone layer, a discovery which led to the Montreal Protocol banning the use of carbon fluorocarbons, which was probably to this date one of the greatest pieces of environmental global legislation that's been enacted. So the science that is conducted in these places is really leading our understanding of climate change and influencing policymakers to a significant extent. However, at Halle, there was a big problem. In around 2000, the British Antarctic Survey identified that the Brunt ice shelf was at risk of fracturing away from the main polar continent. It was locked in position at the top of the red line and at the bottom of the red line, but severe cracks were beginning to appear. And with Halle 5, with its legs rooted in the ice, there was the risk that it would disappear on a giant iceberg. As a result, the British Antarctic Survey decided that they needed to replace the station. And to do this, they decided to hold an international design competition run by the RIBA. They received 86 expressions of interest from around the world. They were then shortlisted down to 6 teams who developed some initial concept designs. from where they then shortlisted down to 3, and those 3 teams worked over a 6-month period before eventually my firm, working with AECOM, were selected as the winners. Before we set about the design process, we wanted to understand some of the challenges of Halle through history. The life of Halle is relatively short. The first station was established in 1957, the International Geophysical Year, and it was a very simple structure, a pitched roof timber hut built on the ice surface. And here you can see it around 4 to 5 years after its completion, virtually buried up to the eaves. It existed like this for another few years. They had to build shafts with ladders to climb down through the roof into the building before it was eventually abandoned. Later structures, and here we see Halle's 3 and 4, were designed specifically so they could be buried. But one just has to imagine the existence in these buried tubes underneath the ice, climbing down a ladder into a place which has got no natural light, where the generators are a constant hum and you can smell the sewage being treated on a constant basis. It must have been a very, very unpleasant life. Added to that, the ice shelf itself moves a bit like water, so was constantly bearing pressure onto these tubes, and you could hear it cracking and creaking around you. So unsurprisingly, this solution of buried buildings was relatively short-lived. Both of them lasted for really no more than 10 or 11 years each. Most recently, new bases have tended to be elevated above the ice surface, and here we see 3 of the most recent stations. The top left is the French-Italian base. I am assured that the French don't live in one side and the Italians in the other. They do actually mix together. The top right is the largest of the all-year stations in the center of the continent. That's the South Pole Station, built by the USA, which has a population of around 50 people in the winter and around 200 people during the summer. The bottom left is the German station Neumayer 3, which is supported on hydraulic legs, which help to jack it up above the rising snow levels year on year. And the bottom right is the Belgian station, Princess Elizabeth, which is a summer-only station, but operates as a net zero carbon base. The challenge at Halle, however, was greater than all those other stations, because not only did it need to be elevated above the ice to deal with the rising snow level, but it also needed to be relocatable, so that if there ever was risk in the future of the station being on the wrong side of a crack line on the Brent ice shelf, the buildings could be moved safe to a safer place inland to continue their operation. Our concept was therefore fairly straightforward. It was for elevated modules on hydraulic legs supported on giant skis, which were both the foundation and the means for relocation. The principle was that virtually all the functions required of the new research station could be accommodated within modules that were around 1,600 square feet, 150 square meters, raised 4 meters or around 15 foot above the snow level, supported on 4 hydraulic legs on large giant skis. And this was used for laboratories, it was used for bedrooms, it was used for offices, and it was also used for twin energy centers containing generators, water treatment, sewage treatment, fire suppression, fuel storage, and engineering offices. The structural design was really very simple. The substructure is formed of a steel space frame that's then supported on the hydraulic legs on the giant skis. And then the superstructure is arranged around the perimeter to allow flexibility for reconfiguration of partitions. And then the whole building is clad in a highly insulated cladding system of glass reinforced panels with a polyisocyanated foam insulation. In terms of the jacking above the rising snow level, the system is simple. Each leg is raised in turn and snow is pushed underneath. Then when that's been done to all the legs, the station can be jacked up around 1 meter to 1.5 meters above the snow level. Something a bit like this. Having worked out that most of the functions of the station could be accommodated in the small blue modules, we realized there were some social functions such as dining, the bar, watching TV, where it's nice to have everybody together, needed a larger special solution. For this, we developed the central module, a 2-story building, which has noisier activities such as dining and the bar downstairs, and quieter activities upstairs for watching TV, going to the gym, and so on. In terms of construction, the centre of activity was in Cape Town in South Africa. But before we started any of the prefabrication or assembly of building components for shipping to Antarctica, we needed to prove that everything was going to work properly. To do that, we built test modules. We built one of the blue modules as a test, and we also built the big red module as a test to make sure that all the cladding would go together, that it would fit on the steel frames, that the hydraulic systems worked, and also that the buildings were as airtight as they were designed to be. And in fact, when we did the airtightness testing, we achieved one of the best airtightness, as I think, that's probably been achieved on any cladding system of 0.1 cubic meter per square meter at 50 pascals of pressure per hour, which is actually a remarkably airtight construction. Once everything was ready, it was assembled on the dockside and then loaded onto this ice-strengthened Russian vessel, where it was shipped to the Antarctica, spent 15 days crossing the roughest ocean in the world, and arrived at the edge of the sea ice, from where these largest components, the steel space frame substructures of the modules, were unloaded and were then pulled by tractor across the sea ice, up the ramps onto the ice shelf and to the site of Halle 5. We used we built the modules at the site at Halle 5 because it meant we could use the existing accommodation to support the construction crew before relocating the base to its eventual location 15 miles further inland. Here we see some of the stages of the construction. Top left, the space frame just arrived on site. It's then lifted by crane onto 2 shipping containers, so that bottom left, the hydraulic legs and big permanent skis can be installed. Then prefabricated timber floor cassettes are installed on top of that space frame to provide a working platform. Then on the top left, you can see prefabricated service runs being installed into the space frame. And then top right, prefabricated elements of plants, that's generators, switch rooms, fuel storage, before eventually the steel superstructure is installed around those elements of plant. On the bottom right, you can see some of the prefabricated rooms being installed, and we had bathrooms, plant rooms, bedrooms, some offices, some laboratory spaces, all prefabricated in the UK and shipped out to Antarctica fully fitted out, just to speed up the construction process, because all construction on this hostile site can only take place in a 10 to 12 week window during the summer months. The cladding, as previously mentioned, is a highly insulated glass fiber system, allowing large panels to be fabricated. Here you can see one of the largest. It's the whole side elevation. It's around 3.5 meters high, and it's around 10 meters in length, fully pre-glazed and fixed back to the steel superstructure. Once all the modules were fully clad and they were largely fitted out inside, they were relocated from the site of Halle 5, 15 miles inland to the site of Halle 6. And here you can see the large red module weighing over 200 tons, supported on 6 legs, lowered down on its hydraulics and then being dragged to the site of Halle 6. It took around an hour and a half to do the 15-mile journey, and then it took the rest of the day just to align the modules one up to the next and then to connect them together. And for the connections, we used highly insulated connectors like you get between train carriages. And here you can see all the modules linked together. So the 3 on the left relate to science. The 2 connected by bridges are actually energy centers. So there are generators in each. There's water production, sewage production, and so on that's shared between them. Then the big red module is the main social space with the dining, the bar, TV watching, and the gym. Next one along is the main command module, which has got the doctor's surgery, the communications area, and the base commander's office. And then the final two at the right are bedrooms, and there's 8 bedrooms in each. Each bedroom is a bunk room, so there's accommodation for 32 people during the summer, 16 during the winter. These are the science modules. As you can see, the furthest left, which looks to the south, has got an upper level. That's for observing the climate. And this is within that upper level, and the guy at the end there, he's using a Dobson spectrophotometer to measure levels of ozone, which are measures which have been taken at Halle now for over 60 years, providing a remarkable data set showing the changes in level of ozone over Antarctica. Moving down the length of the building, this is the main social building. Interestingly, the dark triangles are actually clear glazing, a bit like the dark glazing you get in Ray-Bans. And the white glazing is translucent glazing. That's a double glaze system filled with nanogel, which was invented originally by NASA to insulate the space shuttle on re-entry to Earth's atmosphere, but which we found to be a fantastic transmitter of daylight whilst preserving high levels of thermal resistance. And this is the consequence internally. You can see a very bright, luminous, double height space, which provides the heart of the station. It's where the pool table is, but actually in the summer they move the pool table and everyone drags the dining room tables into this area because it is so nice and light with good clear views out onto the ice shelf. This is the staircase leading to the upper level. And just to remind us all that this is the UK's research station, we have a picture of the Queen on the left-hand side. The staircase is actually lined with Lebanese cedar panels, which give off a nice scent. There are so many psychological and sensory deprivations working in the Antarctic, one of which is the smell of things like trees and flora and so on. So introducing a panel which has got a nice scent was seen as just one small way that we could make people's life a little bit better living in this bleak landscape. And this, the upper level, a quieter meeting and reading space. And that big oval roof light there allows people to stand in there and during the depths of winter admire the fantastic displays of the Aurora Australis or Southern Lights that you get at Halle. Moving down to the north end of the station, we find ourselves moving through corridors. The corridors themselves have got roof lights above to bring natural light into the heart of the space. Each building is identified with different colours that would palette of which was developed with the help of a colour psychologist, Angela Wright, to help people beat the effects of seasonal affective disorder. The bathrooms all use a vacuum drainage system to cut down on water usage, which is obviously energy hungry, through the use of low water use fittings, vacuum drainage, and also people limiting the amount of time they spend in the showers, etc. We've managed to cut water usage down from 120 litres per person per day at Halle 5 down to just 20 litres per person per day at Halle 6, which has had a significant impact on energy usage and therefore the overall environmental footprint of the station. And here's one of the bedrooms. The bedrooms are bunk rooms, so you share a room during the summer and you get a room to yourself during the winter. They've got plenty of storage, a desk, a good view out with blackout blinds to cut out the daylight, which is of course 24 hours during the summer. And this is the view of the end of the station after all the building has been raised up, the snow has been flattened out, ready for another winter season. And here we see it in the middle of the winter, and you can see how the wind has blown underneath the buildings, creating a big drift on the leeward side away from the skis, and that this wind has accelerated underneath, keeping the skis themselves clear of snow, allowing for adjustments and also for the raising above the rising snow level. We've been lucky that the building has received a number of awards. It's featured in lots of publications. And of course, the proudest thing is it's the subject of a book written by Ruth, which is available through all good booksellers and is highly recommended. The other benefit that we have gained from our work on Halle is to be able to work on a series of other Antarctic stations, bringing the experience of one to bear on the other. Of course, each of them has special challenges. The station which followed on from Halle that we designed was Juan Carlos I for the Spanish government. It's on Livingston Island in the archipelagos off the Antarctic Peninsula, so further north. This is the site of Juan Carlos before it was redeveloped. So it's a summer only station. People were living in a combination of small glass fiber igloos and converted shipping containers. In the winter, it would get around 3 meters of snow, and then during the summer, all the snow would melt. Winds in this location blow from every single direction. It's also the site of a very diverse but fragile ecology. There are leopard seals, elephant seals, gentoo penguins, and there are also very rare mosses which grow on the site of Juan Carlos I, with plants in Antarctica being very rare in themselves. So ensuring that there was minimal impact on this ecology was a key project driver. Bearing in mind that the winds blow from every direction, we thought very long and hard about ways in which to encourage social interaction. Our concept was therefore to create modular wings joined around a central core, which would mean that people would always be passing past each other in that core area, stop and have chats and so on. This is the design, which shows big glazed elevations at the end of each one of the wings looking out into the fantastic Antarctic landscape. The buildings are raised up so that when the crew arrive at the start of the summer season, they climb up the ladders. The base is all snowed in, and then as the snow melts, then they can access the buildings through the doors at the lower level. And here we see the completed base. It was actually occupied for the first time just 1.5 years ago, and is now delivering fantastic science for the Spanish Ministry of Science and Investigation. More recently, we've been working on 3 projects at the same time. The first of these is another project for the British Antarctic Survey. It's at their largest base, Rothero Research Station at 67 degrees south on Adelaide Island, which is a stunning Antarctic setting with mountains and seascapes all around. If you go for a walk here in the evening, you'll hear whales out in the sea, you'll hear them blowing, you'll see multiple different types of seals and penguins and so on. This is a very busy research station. It's used as a logistics hub, both by the UK, but also by other nations who will land at the runway before moving on to other locations on the main Antarctic continent itself. A new wharf was recently constructed here by BAM to support the British Antarctic Survey's new research vessel, the Sir David Attenborough. And the redevelopment of the station is now on progress, which is consolidating activities to also support the actions of the research vessel Sir David Attenborough. This is the building that we're involved with. It's called the Discovery Building. It's a science and operations building. So it includes offices for scientists, it includes administrative offices, comms areas, it includes science prep areas, it includes the main plant spaces, the main medical facility and recreational facilities, and also this control tower, both for looking after marine operations, but also for comms related to air activity of people landing at the runway and then traveling on into the main Antarctic continent. It's a ground-based building. So that large vehicles such as bulldozers and so on can access into the vehicle workshop and also into the science prep areas. It's got a monopitch roof. The wind blows from the left-hand side. It's got curved eaves so that the wind flows over the roof. And then you can see where the sign is, the British Antarctic Survey sign. There's a strange protrusion. That's actually a wind deflector, so that the wind blows across the roof and then is captured by the deflector and then channeled down the leeward facade of the building. And then at high velocity, that will help to remove snow from the leeward side so that the doors that access the building on that side don't get jammed up with drifting snow. And you can see that quite clearly at item number 6 in this cross section through the building here. The building is currently under construction. The groundworks were completed last season, and just recently a crew of 20 people did arrive on site to install the concrete pad foundations and to get some of the early sort of lower level construction carried out to allow for a fulsome construction season next year. In order for those 20 people to reach Antarctica, they had to isolate in the UK for 3 weeks. Then they went by ship down to the Antarctic on a 11 to 12 week journey. They then arrived in the Antarctic, where they'll have another 10 weeks of construction, and then they'll repeat the whole process returning to the UK. So it shows remarkable devotion to achieve just that 10-week construction process. The other project I'm going to talk about just briefly is Scotbase. This is a project for Antarctica, New Zealand. It's the largest project which we've been involved with in the Antarctic. We started working on this in 2017 in a joint venture with a New Zealand firm of architects called Jasmax. This is the existing Scotbase. Scotbase was established in 1957, the same year as Halle. In fact, it was established in the same year as Halle because it was part of an expedition organised by Sir Vivian Fuchs and supported by Sir Edmund Hillary. The idea that Fuchs would drive from Halle across the South Pole, across to the site of Scotbase, and that Hillary would lay supplies for Fuchs so that once he got to the South Pole and beyond, he would be able to pick up food and fuel supplies to enable his journey on to Scotbase. As it transpired, Hillary was rather quicker off the mark than Fuchs and arrived at the South Pole before Fuchs, which led to a slightly fractious friendship between the two, because Fuchs had wanted to get there first, but in the end the expedition was a great success, and the consequence was that Scotbase was established. The buildings that you're seeing here are the second iteration, which were built during the 1980s. They're steel framed elevated buildings with metal composite cladding, reaching pretty much now the end of their life, but in a spectacular location on a place called Pram Point, overlooked by Mount Erebus, which is an active volcano. Some of the issues that exist with the current base: it's on multiple different levels, which makes it very inefficient. So every time you reach one of these half staircases and you're doing a resupply, you have to unload your trolley, carry it up by hand, reload another trolley. The services are in very small voids and are therefore difficult to maintain. Much of the equipment is very old, including the water production plant. The fire safety is compromised in a number of locations, and you just have to imagine yourself escaping out of that door on the bottom left and having to fling yourself round onto the ladder to get down to the ground. The orientation of the buildings leads to significant snow drifting, some of which occurs on the roof and therefore has to be cleared by people climbing onto the roof, which of course is too dangerous. As a result, we began a process of intense stakeholder engagement to come up with concepts for a new base development. And here you can see some of the early sketches investigating buildings in a line, elevated buildings, buildings stepping down the hillside. In the end, the selected solution was for 3 buildings parallel to each other, perpendicular to the prevailing wind, which blows, or the strong winds, sorry, that blow from the southwest. Buildings that are elevated to allow the wind to channel underneath and clear away any snow that might drift around. The lower level of the topmost building connects to the upper level of the middle building. The lower level of the middle building connects to the upper level of the bottom building, and each has stairs and a hoist within. And the form of the buildings, with a monopitch roof and aerodynamic eaves, minimizes the impact of wind on the structure, and also again ensures that the wind can be utilized to clear away any snowdrift in the immediate vicinity of any of the buildings. To prove this concept, we did snowboard modelling in the laboratories of RWDI in Canada, where they place models into a water flume and then drop fine sand in. Then a current is introduced. The fine sand will then move like snow across the buildings and drop out around them to simulate snow drifting. To calibrate this, we put in a model of the existing base, which you see top right. And when we were happy that the snow was, or the sand was drifting around the buildings in the same way that snow would, we then put in some of our variations to see how the buildings would perform. And we tried different configurations. It's a highly iterative process to come out with the optimum arrangement of buildings relative to each other to determine the site layout. So we move from the existing base to this arrangement of 3 parallel buildings connected by bridges, elevated and aerodynamic. The topmost building provides accommodation, the middle building is for science and administration, and the bottom building is used for operations, workshops, stores, and so on. Some of the other features that you see around the site are helipads. There's quite a bit of other storage for fuel, for vehicles and for snowmobiles and so on. And there's also remains of Hillary's original 1957 hut, what's called the Trans-Antarctic Expeditionary Hut, which was recently beautifully conserved by the New Zealand Antarctic Heritage Trust. Here the building in the context of Pram Point. A key part of the project has been integration of Maori and New Zealand cultural design, particularly into the interior. And in happier times when we could travel to New Zealand, here we are with the design team doing an overnight stay at a Maori marae in Christchurch in what's called a hui, where we discuss the importance of Maori design features and also of the ways in which we can integrate the culture of New Zealand, also the culture of exploration in Antarctica of New Zealand into the design of the new base. As I said, we were particularly conscious of the input of Sir Edmund Hillary's base from 1957, and here you can see the restored building and some of the colours that his architect Frank Ponder used to help alleviate the impacts of seasonal affected disorder. And then of course, because it's a New Zealand base, it also features pictures of the Queen and Prince Philip. And here how some of those concepts have been transferred to the design of the new base. So this is in the main accommodation building. This is the circulation at the heart of the base, which also provides a gallery for the photographs of all the winterers who have spent time working at Scott Base over the last 60 years. You can see that central double height space, item D in this cross section. The lower levels are used for functional spaces, plant rooms, food storage, and so on. And the upper levels are used for living accommodation, whether that's single bedrooms or shared bedrooms for short-term visitors. This is a typical long-term single bedroom, which is compact. They're around 2 meters wide by around 3.5 meters long. It has a wardrobe, bed with lots of storage under, a desk, lots of pinboard for putting up pictures, a window with a blackout blind giving you great views out onto the landscape of Ross Island where the base is located. The dining room and the bar are joined together, and they have a timber ceiling. There's also a big window looking out towards Mount Erebus. It's really important in these bases to connect people to their landscape, not only because it's very beautiful to see, but also to remind them of the isolation, fragility in a way of the environment and the challenges that that environment poses, almost as a way of ensuring their health and safety. Quiet space is an important part of these facilities as well, spaces that people can sit, read a book, contemplate where they are, just quietly be on their own. So this library at one end of the building is an important ingredient in ensuring people's well-being. Bridge links connect each of the buildings. The bridge links as well provide views out onto the landscape. Services connect between one building and the next in those panels underneath the windows, all of which are removable to allow for easy maintenance. This is the collaborative workspace in the middle building, which is the science building, where scientists can work together, exchange ideas. There are labs off to the left and offices and administration off to the right. These bases are really an interesting sort of mix of facilities. On the one hand, they're like a hotel with bedrooms, dining rooms, bars and libraries. On the other hand, they're almost quite industrial. This is the science prep area where people will get everything ready before they go out to expeditions in the field. So they'll be putting a lot of electronic equipment in here, all their tents, their sleeping bags, getting their food for their expedition ready, and so on. So they need to be quite flexible, adaptable spaces. This shows the three buildings together. The buildings B and C both have decks on the top. One is for telecommunications and the other is for science equipment. In building C, that's the most industrial really of all three buildings, and probably the most industrial space is this vehicle workshop, which is used for maintaining the fleet of vehicles, which is so essential not only for the maintenance of the base but also to support the expeditions going out in the field. And there are some quite special vehicles, whether that's skidoos or piston bullies like you see on ski slopes, or these haglans that you can see elevated up on the hoist there that are used to carry people out into the field. The building envelope is a combination of metal composite panels with insulated GRP to form the most aerodynamic elements, such as the junction between gables and the main fuselages of the building. There are piled foundations and, of course, the aerodynamic form. In terms of delivering the Scott Base redevelopment to the site, we're really pushing the boundaries. The building will actually be built in New Zealand. It will then be split into very large modular sections and then transported on a big ship where you can see as a whole building in the top picture there. Once it gets to site, we will then use most special motorized transporters to then deliver each of the modules into position and then link together. And this process will save an enormous amount of time on site, cutting it from a traditional construction by around 3 or 4 seasons. And it's expected that construction will be completed around 2027. Finally, this is our most recent project. It's the redevelopment of Davis Station for the Australian Antarctic Division. Davis Station sits in the Vestfold Hills and has been in operation again since the 1950s. Many of the buildings there are also reaching the end of their life. So we've been working with the AAD on a master plan for the next 50 years of life at Davis. Our concept is to come up with a modular solution, elevated. It really combines together many of the features that have been apparent in the previous 4 projects which I've shown. It'll be highly flexible, simple to maintain, elevated to reduce the amount of snow management that's needed on site, highly sustainable, drawing energy from wind and solar power, with a big focus on well-being and providing fantastic facilities to support science, some of which, of course, we have no idea what it will be looking at in 50 years' time. So therefore, the real pressure on creating flexible facilities to support anything from robotics through to drone activity to unmanned submarine research. The multiple buildings of the existing station will be rationalized to 2 building types. The elevated buildings are used for sleeping, for living, science and technology, operations and utilities, with ground-based buildings for vehicle workshops, for storage, and for water production and so on. Internally, the idea is to use natural materials to remind people of home. So timber that might be sourced from Australia, but also with good clear views out into the Vestfold Hills, potentials for using hydroponics to provide fresh fruit and veg during the winter season, and a comfortable lighting environment which responds to the circadian rhythms of people living through 24-hour daylight and 24-hour darkness. So here you see the site of the existing station, made up of multiple buildings developed in a haphazard way over 60 years, resolving to a more ordered arrangement of elevated craft oriented in the direction of the prevailing wind, which can then blow underneath, removing snowdrift away from the buildings and minimizing the environmental impact by comparison to the existing, with the use of sustainable energy sources such as wind and solar, and really cutting down the amount of fuel that's needed to support the base through the year. And here you can see the impact of that design during the winter. And I think with that, that is my last slide. So I'll pass back to Ruth. Thank you very much.
Thank you very much, Hugh. I'm feeling a bit chilly now because we have been spending 40 minutes in the Antarctic, but it was absolutely fascinating. And I think we're going to have a chance in a moment to warm up a bit with our next presentation. But first of all, can I remind you, please, if you do have questions, and I'm sure you do, either for Hugh or for Jonathan, our next speaker, just press the button and send them in, because we will be using the questions at the end of the session. So I'm delighted now to introduce Jonathan Lowy of VM ZINC, who is going to take us on a tour of the world, I believe, looking at projects using zinc and particularly how they can work in extreme environments. Over to you, Jonathan.
Hello, welcome everybody to this webinar from Paris to the end of the world. We're going to look at some zinc projects in some extraordinary locations. And this first image is obviously of a fjord in Norway, near Loen, where the Alexandra Hotel has this spectacular viewing platform, which combines zinc and other materials such as timber and glazing. Moving forward a little bit, but before we go in depth into some projects, just wanted to let you know sort of really what we do. We actually refine the zinc. So on the top right, you can see hot liquid zinc coming out of the oven. That gets rolled into natural zinc coils, which you can see on the top left, before being pre-weathered. The bottom left photo is an interesting project from Holland, where old and new's been combined. You can see pre-weathered pigmento red standing seam zinc roofing connected with a very attractive glazing unit to an old thatched cottage. And on the right, again, the same zinc, but this time in pre-patinated quartz on a facade near New York in the US, where the whole facade is made out of zinc. The cornices, the soffits, the framing, the whole facade is all zinc. We always have to have a little bit of a thought for this man, Baron Haussmann, who was asked by Napoleon III to redevelop Paris, to take it from a medieval city into a modern city in the middle of the 19th century. This happened just a few years after VM ZINC was founded in 1837, and Haussmann did his development in Paris in the middle of the 19th century, about 1850 to 1860. And many of the grand boulevards, which you can still see today, have zinc roofs. About 99% of all these roofs have some zinc on them. And you can see the top left-hand corner is the Étoile, the Eiffel Tower, sorry, the Arc de Triomphe. The top right is the Gare du Nord, the bottom right is the Gare de Lyon, and the left, which could well be a station in Paris, is actually Brighton railway station, which is a very historic railway station, which was redeveloped using very similar techniques. And this was an extension or a renovated part of the building that was done in the end of the 20th century, about sort of 2000, using batten cap roofing. Staying in Brighton and the railway theme, this is Volks Electric Railway, which is actually, as you can see, on the beach. Zinc performs extremely well in marine environments. It performs very well against salt. And here, Azingar, which is actually engraved zinc, has been used again to clad the roofs and the walls using standing seam. Staying close to the sea, but a bit further north on the beautiful Isle of Skye, is an artist studio called Midden Studio. Here, again, standing seam zinc is used on the roofs, on the walls to clad this building. The difference here is it's natural zinc, and you can see on the top right some of the almost texture of the patina forming, which is not uniform. It takes a few years to form to become a middle grey. The other interesting part of this project is that the panels have stamps on them. It almost sort of looks like a noughts and crosses pattern. Zinc's relatively soft, not like lead, but it can be worked and stamped and formed. So you can create these interesting patterns and do these, create this image. And although it's not Frank Lloyd Wright's Falling Water, there is a feel of this waterfall which is visible from the studio. You can see on the right where you can actually look through into the river beneath, and on the left you can see the opening where that window has been created. Staying in an area of the world which can get very, very windy indeed, this is a church, St. Martyrs Church in Harvey, just south of New Orleans in Louisiana, and it was designed and built by Escu Dumez Ripple in 2003, just over a year before the Katrina hurricane disaster struck. And you can see on the right the quartz pre-weathered zinc standing seam cladding and blown out windows and peeled off roofs. After the hurricane, the building was inspected and the zinc was almost entirely intact. So it really has been hurricane tested. Moving slightly to a different environment, this is Kiruna in Sweden, north of the Arctic Circle. So at this time of the year, probably very, very long nights indeed. And here you see pre-patinated flat lock panels. You can see the panels on the right. They interlock quite simply, and you can create curve forms and straight forms. And there's all the detailing around these interesting round windows that's been created in this very, very extreme cold environment. Keeping the snowy theme, but moving further south, this is a refuge in Andorra, high in the Pyrenees, where the architects have created this super insulated box, which is then clad with standing seam roofing and cladding. And on the south facing face, there are PV panels and obviously the window openings. And you can see altitude 2,488 meters. So in the winter, very, very cold and snowy, but in the summer, it does actually get very hot. So a big change in temperature, going from hot sun to very cold snow, wind, and so on. So fairly extreme. This time going even higher though, 3,700 meters in the Himalayas, Lhasa in Tibet, where a hotel was built on a little bit on the theme of a monastery, using a vernacular architecture, but combining it with batten cap roofing. Which is not entirely dissimilar to the batten cap roofing that you'd find in Paris. Now we're staying in Asia, but probably going to one of the coldest places in the world. This is Yakutsk in Russia, which has a population of about 300,000 people. The coldest permanently inhabited city in the world, built on permafrost. You've got most of the year it is well below freezing. And in 2003, we were contacted to get involved in a project for the local circus, of all things. And again, standing seam pre-patinated quartz zinc panels were used to roof this building. One of the differences here was that a double ventilated roof was built. This means that you don't get a buildup of any humidity which can turn to ice, condensation, which would then create potential problems, not so much for the zinc, but more the roof structure. And this has been in place for 17 years. Now, zinc, like all metal, is cold brittle. So if you did try to install it at -50, it would crack. But once it's been installed, it's very resistant to these extreme temperatures. Going from cold to hot, this is Phoenix in Arizona, in the south of the US. Probably one of the hottest cities. It can get close to 50 degrees in the summer. And this police station has a rain screen, again in pre-patinated quartz zinc, using perforated panels which reduce the solar gain on this building and also give an interesting texture and can be backlit, as you can see. Staying in a warm environment, but this time in Singapore. This is Theatres on the Bay, designed by DEP architects almost 20 years ago now. Right on the sea, always hot and humid. The atmosphere was probably not really one of the main problems for the zinc here. It was more the detailing, very low slope roofs, complicated junctions, a bull nose. But again, the malleability and workability of zinc allow these types of shapes and roofs to be clad very effectively in zinc. Staying by the sea, but just giving you a few examples of different areas where zinc's being used. On the left is Bondi Beach in Australia. In the middle, St Andrews on the north coast of the UK. And on the right, Terry Farrell's Kennedy swimming pool complex in Hong Kong. All of these right on the sea, and they tend to get quite windy. Certainly Hong Kong and St Andrews, there are extreme winds, but the zinc resists all these environments extremely well. Talking about resisting wind, it's obviously important to get the design right and the installation, and by using the right number of clips and spacing these clips at the right centers and using the right width panels, pretty much any environment, as we've seen, can be clad with zinc panels. And on the right you actually see a test which has been done at Wintec to do some actual testing of the zinc panels. Just going to finish on an interesting project, which is the Lighthouse at the End of the World, which Jules Verne based one of his books on. This was actually a real lighthouse that sort of became a little bit derelict and almost fell down. And a French explorer wanted to recreate the lighthouse, which is very close to Cape Horn. And he got a group of companies together, including VMZINC. And this was rebuilt in the late 90s with a zinc roof and a zinc ornament, and has been there ever since. And obviously in the region of Cape Horn, not only is it by the sea, but you get incredibly strong winds almost all the time. There was a slightly smaller model of this also built in La Baie of La Rochelle in Western France, slightly more accessible. But again, this shows how well zinc deals with a marine environment. It's actually almost in the sea. Right, well, that was a short review of some extraordinary projects in some extraordinary places. But if you would like more information, samples, literature, technical details to discuss your own projects, we'd be very happy to do so. So just give us a call, drop us an email, go on our website. Thanks.
Thank you very much indeed. That was absolutely great. And I think it was wonderful to see how well zinc can work in so many difficult circumstances, and also how lovely it can look. And we've had questions coming in. I'm just having a look at some of them. Here's one for Jonathan. Can zinc be a long-lasting option for Atlantic-facing environments with harsh, salty winds in the Caribbean? And the questioner says, local advice is that metal roofs always corrode.
Well, metal does corrode, that's quite accurate, but different metals corrode at different rates. Steel corrodes fairly quickly in salty marine environments, but zinc far more slowly. Zinc's been used in marine environments for decades and has actually already been used in the Caribbean. So zinc on a roof in the Caribbean would not only resist the winds, hurricanes, but also the salt. So it would be a good solution, and it would also be a very durable solution, which would probably require relatively little maintenance. So yes.
Oh, that's fantastic. And then there's a question which says, the location of the property on the island of Col is on the island of Col in the Outer Hebrides, approximately 500 feet from the sea. Can pigmento storm grey be used? That means
well, pigmento is zinc with a pigment in it, so it has a slight colour. Right. And we've recently launched another couple of colours, which storm grey is grey with a very slight redness. So yes, it can be. I mean, it's I showed the project on the Isle of Skye. The Isle of Col is quite close, so it can be. The only thing I would say is that whilst zinc is extremely resistant to salt, if you put it on a non-rinsed surface, it is possible for the salt to sort of almost stick to it and show itself, so it acts as a stain. But on any roof, it would be absolutely fine, or any rinsed facade. So that project on the Isle of Coll with Storm Grey should be fine.
That's great. I'll come back to you, but we've got questions coming in for Hugh as well. First one I'm going to answer because it says, appears no cooking kitchen facilities are provided. There are fantastic cooking and kitchen facilities, and they keep eggs lasting longer than you could possibly imagine. But that's the only question I'm qualified to answer. I'll put the others to Hugh. And there's several questions that have come in which talk about how the lessons you've learnt from these projects in the Antarctic, whether to do with management of a work team or other things, how they apply to work that you do in less extreme environments. And I know you've obviously done a great deal of work here more recently and won quite a lot of awards for it. So I'm guessing you learnt something.
I hope so. I think the key really has been around sort of designing from first principles, which I know sounds sort of pretty obvious if you're an architect, but it's certainly something which has been really important in the Antarctic work. Sort of thinking absolutely about how people are going to live and work in these environments. You know, right from the moment they wake up, what's the surface under their feet? How do they? What's the journey they make to get their food? What's the most efficient way to organise their workspace? And then thinking about how that sort of dovetails in with resisting the environmental, the cold weather, the winds, and so on, and then tying that all into the logistics. So it's a very sort of holistic way of thinking about design, and I think that has definitely permeated into the projects that we've done in the UK. The other aspect is just seeking opinion from as many people as possible. I've always been rather relieved, actually, when we've worked in the Antarctic, that there are loads and loads of checks and balances on the work that we do, and always the clients are super interested in every single aspect and want to understand why do we think that would be good for someone's psychological well-being, or what would that detail do that would be better than what we've done before in keeping the weather out. And I think that sort of level of investigation and level also of engagement with clients has been a really big part of the work in the Antarctic, and has definitely impacted upon the way we approach projects in the UK. So I think sort of it's a two-way thing, sort of holistic, sort of first principle sort of forms of design, but also just maximising the amount of engagement with clients and users of the buildings.
That's great. And actually someone asked a question about post-occupancy studies, and I assume as part of that ongoing research you've carried those out, have you?
We did do a post-occupancy evaluation at Halle shortly after it was finished, which was really beneficial. We generally got very good response on every single aspect of the design. It was slightly tied up with a sort of moment of transition and of the winter crew at the same time trying to negotiate different forms of passage out of the Antarctic. Some of them wanted to spend some time in South Africa, some of them wanted to go via South America. So that did actually impact a little bit on the quality of the answers that we got. But nonetheless, you know, the responses about things like lighting, colour and so on were really useful. I think it's something which we would try harder to get really good information from on the projects we're working on at the moment, because I do find that as we're designing the new projects, whether it's for British Antarctic Survey, Antarctica New Zealand or the Australian Antarctic Division, that we do draw a lot upon each project in turn. So I find often that I'm talking to Antarctica New Zealand saying, oh, for the British we're doing this, and they're going, oh, that's an interesting idea, have you thought about doing it like that? And all the projects are sort of feeding one to another. So I think that if we can carry out really good quality post-occupancy evaluation on those projects, it will also really positively impact on any future work that we do too. So it's a really important part of the design process.
And I've got a more technical question for you now. Somebody's asked, how are the buildings heated, and does ventilation cause problems because of the external temperature?
So the forms of heating, they actually vary between the different projects. So at Halle, the heating is provided because we've got combined heat and power generators. So the generators provide the electrical power, but the heat that they give off is captured and then used to provide the heating within the base. And although there are boilers, they're only there as a kind of like an addition to the sort of heating load if ever there's insufficient power being generated. But so it's primarily off the generators. The buildings are incredibly well insulated, so they have very low U value, so that actually reduces the heating load. At the New Zealand base, Scott base, it's powered, probably around 70% of the power comes from a wind farm, which is shared with the American station McMurdo, which is very close by, just 3 kilometres away. And so there, all the heating is provided by electric boilers. So it just depends on the situation, what the heat source is. And I know this isn't at all the question that's been asked, Ruth, but it is just a demonstration that, you know, one might look at these Antarctic projects and think, oh, it's one size fits all. You know, that must be easy. Once you've done the first one, they're all going to just flow off the production line. But what we do find is that they all come with very, very special requirements. And whether that's energy, whether that's the climate, and or whether it's the culture of the people that are going to occupy them. And that's been one of the kind of like great fascinations, I think, of the body of work that we've carried out.
That's great. I'm going to go back to Jonathan for a moment, and I've got a series of questions which I think really are to do with, again, with zinc lasting. And I'm going to put them all to you, and perhaps you can give me a sort of portmanteau response, because somebody asked about the expected longevity of a zinc roof or wall, and do the atmospheric climatic conditions affect this? Another questioner has come in, and I know you dealt with this slightly, saying, is zinc cold brittle? And I guess there's a question not only about what it's like in use, but also applying it. I mean, could you have applied it in the Antarctic? I don't know. And also it says, somebody says, in terms of delivering robust details, does zinc need to be installed by a specialist? So can you have a bit of a look at all those, Jonathan?
Yes, Ruth, I'll give all that a go. As far as the durability, as zinc's been used for over 200 years, we do have quite a lot of knowledge about the corrosion rates and the performance. Liverpool Central Library, which was the Picton Reading Room, was built in 1879 with a zinc roof, and it was replaced in 2012. So that we could actually do some quite scientific analysis on that. And we worked out the corrosion rates. Liverpool, obviously, at the end of the 19th century, was a very different atmosphere to what it is now, mainly because of coal being burnt and SO2, so acid rain, which is probably the thing that will attack zinc more than anything else. And we have all sorts of pollution problems in the world, but probably acid rain is probably lower than it was certainly 100 years ago. So the zinc corrodes, but it will, in most atmospheres, it will last over 100 years. As far as being cold brittle, yes, zinc is cold brittle. All metals are cold brittle, and you cannot install it at -50. It will just break. But I was on a job site in Montreal many years ago, and zinc was being fitted at -20. And basically what the installers were doing, they were taking the panels from within the building, which was heated, putting them on, and putting about 3 or 4 panels on and closing the seams before the metal lost its temperature, which actually worked. The installers couldn't really install more than that either, because they were also losing their temperature, and at -20 working outside is quite tricky. Going on to installers, absolutely, zinc has to be installed by a specialist contractor. It is not a general trade for a general builder. Zinc is quite similar to stainless steel, to copper, so it doesn't need to be just somebody that only does zinc, but it can't be done by a general builder.
Thank you very much indeed. I'm going to put another kind of portmanteau question to Hugh, and I suspect the answer will be quite long, and I suspect this may be our last question. There's a couple of technical things that have come in. One's asking about fire strategy, which obviously, you know, we're all very fire aware now. And another's asking about quite how you made the huge savings on water at Halle. That's on the technical side. And the other thing that people have asked, and I sort of half know the answers, but I'd love to hear them from you, were about site visits. Did you get to the site? How much did you actually get to visit the projects, etc.?
Great. Well, I'll start with the fire because that's always the most difficult one. Coming up with the right fire strategy is quite challenging, and fire is a massive problem in the Antarctic, primarily because, of course, there's no fire brigade, and different nations have different strategies as to how to deal with fire. So, for example, the British Antarctic Survey and the Australian Antarctic Division tend to they will train people how to deal with fire, but the purpose of that is in order to get people who are at risk out of buildings, but it's not to save the buildings themselves. Whereas Antarctica and New Zealand have training with the New Zealand Fire Service to actually put out the fire and save the building as well, which is quite a different kind of strategy. And I think the reason why Antarctica and New Zealand do that is because they are supported by the US Antarctic program at McMurdo Station, which is very big. It has a population of around 1,000 people in the summer, and they actually have a dedicated fire service, which is staffed by qualified firefighters who are sent out from the US, and they have 2 fire engines there as well. Nonetheless, the key always is prevention. And so on the one hand, there's measures like all of the buildings that we've worked on have sprinkler systems, generally high pressure water mist systems, so that they're on a double knock system. So they're empty of water, which is then sent as a mist at high pressure and sort of reduces the oxygen level where the fire source is to starve it and help to put it out. But they also obviously have all the latest sort of sensing equipment and so on. But of course, an enormous amount of work also goes into passive fire design, looking at fire compartmentation and also looking at materials, and then specifically testing things like facades to make sure that they will meet the criteria which are set out by fire engineers. So, for example, on the project that we're working at the moment with the British Antarctic Survey, we're going through fire testing on the metal composite panelling system at the moment. We'll do exactly the same on the New Zealand base. And, whereas in the UK, you might rely on historic test data, in the Antarctic, because of the dangers and because of the limited numbers of staff and the limited skills in putting out fires, you actually will test every single building component. So there's quite a big part of building budgets assigned to fire testing, as well as testing climate for sort of air infiltration rates and so on. I think the next part of your question was about, was it about driving down water usage? I think it was.
Yes, it was.
So the obviously creating water uses an enormous amount of energy, and it's the way you create the water is different according to the different sites. So at Halle, for example, ice is shoveled into basically a giant ice melter, like a kind of kettle, I guess, and it's melted to create the water. So that uses quite a bit of energy. So reducing that water usage is really important. At Scott base, the New Zealand base, and Davis, the Australian base, they use reverse osmosis, so desalinating seawater for water usage, which again is very energy hungry. So cutting down water usage is really important. And the ways that we've found best to do that, there's sort of 3. One is very simple. It's just to do with the sort of taps and fittings that you use, and make sure that they provide aerated water to reduce the amount of water when you're running the tap, just generally. The next one is using vacuum drainage, like you get on an aeroplane or a ship. So rather than using kind of like 8 or 9 litres of water for a flush, you're using around sort of 1 to 1.5 litres. So that has a really significant role to play in reducing water usage. And then the third thing is just management. It's saying to people, when you have a shower, you're going to have to shovel the snow to make the water. So maybe don't have it on for too long. Maybe, 2 minutes is probably enough. Once you've soaked up, maybe turn it off, keep going, then turn it on when you want to get rid of the soap, those kind of things. So that also has quite a big part to play in sort of driving down the water usage. So, but it's something that's really kind of knocked into you when you do go on any of these stations, is just responsibility, in particular for water and power. And then
Great.
last thing I think you asked me about was site visits. So
Yes.
that is definitely a perk of the job. I've actually been down to the Antarctic 5 times, which each time has been to different places. We've visited lots of different bases. I think visited sort of 9 or 10 different bases, which is also really good for the research. Visiting Halle is a very special kind of experience because it's just so bleak and apparently featureless when you get there, but you just sort of in the end start to really sort of almost fall in love with the cloud formations, the way that the wind plays across the ice surface. It's actually a very sort of de-stressing kind of environment, I find. Whereas some of the other sites, the Spanish site or Rotherham, the other British station, are just stunning scenery and amazing wildlife. So you do get incredible experiences going to any of the stations. And then you go to the New Zealand station, Scott Base, and you're just surrounded by the history of exploration. So not only is there Hillary's hut right next to the base, but there's also the possibility of visiting Shackleton's Nimrod hut or either of Scott's huts related to both of his expeditions. And going inside any of those huts, you just feel the sheer weight of history upon your shoulders and the impact of, that kind of exploration, in those early days, and how cold they must have been, and with equipment which is only a shadow of what we have available now. And I find that really a very kind of extraordinary and sort of enlivening experience, I guess. So
Well,
I hope that covered off all 3 areas.
It did, absolutely. And I think we're all feeling enlivened and uplifted. There were a couple of questions that came in that were very specific to 1 or 2 of you, asking for some more details about things. And I'm sure those could be passed on to you. And you can answer those specifically back to the people who've questioned them, because we really have run out of time. I know everybody's got very busy days, and probably a lot of the viewers have got more things scheduled in. It's great that so many of you have been able to come and watch this. And I think it just remains for me to say thank you very much for attending. Thank you very much on behalf of Architecture Today. Thank you to Hugh. Thank you to Jonathan and to VMZINC. There will be more events, and I hope to see some of you at some of those. Thank you very much indeed. Bye.